Hey there, wanted to let you know this is an audio only podcast, and if you get your podcast on Spotify, you can go follow me there. All right, cheers. Hello there, ladies and gentlemen. Welcome back to the Ephemeris podcast. I'm your host, Ophelia, and thank you for joining me in episode 23 of chapter 2. And as usual, we're going through some recent news in the world of astronomy. And the first article we'll be looking at is the latest ancient mystery to be solved. And the second article will be about new findings in the Serpens Nebula. Last one will be about recent discoveries on the evolution of black holes. So, without further ado, let's jump right into our stories today. So, scientists have finally cracked the Antikythera mechanism. Hopefully, I'm saying that correctly. It's a Greek name, and I'm not that great with names, so apologies if I've completely butchered that. But this is a mechanical computer and bronze device from 2,200 years ago that is considered the world's first computer, and it was first discovered in a shipwreck in 1900 underwater near the Greek island of Antikythera, hence the name. And it dates back to either 100 or 200 BC, so during ancient Egyptian times. The lore behind this discovery is actually kind of funny because, as the article has stated directly, quote, the mechanism is so sophisticated that some thought it had to be a modern device that got mixed in with the ancient artifacts that they found in this shipwreck here. And so the mechanism kept track of the dates of celestial objects using a clock with interlocking gears. I believe there's 30 of them. And it had like rings and evenly spaced holes. But the mystery for the mechanism was how many holes did it actually have? We weren't sure how many it had, and without this info, scientists weren't able to figure out which calendar the clock was based on. So recently, using some statistical modeling, some university astronomers were able to determine that the clock was based on a lunar calendar rather than an Egyptian one. However, this is a development that took like several years. It didn't happen immediately. The first part of the discovery, and there are like parts of the discovery that were made by different individuals, but the first part of the discovery, it was in 2005 when X-ray computed tomography was used on the object, and that information was used by several researchers because it helped them determine the internal structure, and that's what told us that the device was used for celestial events. But the details from the analysis is what allowed YouTuber Chris Budiselic, an enthusiast, of the subject, to measure the positions of the holes and propose that the mechanism had between 347 and 367 holes. Now, this was too large of a range to pinpoint which calendar it was using. It really could have been either the Greek lunar calendar or the Egyptian calendar. So Graham Wowen, I think that's what the person's name was, and Joseph Bailey from the University of Glasgow. They followed this up with a modifying technique that was purposed for gravitational waves, and they were able to narrow down the range to about 354 to 355. And so if it had been like 365 or so, then we would know it would have been like the Egyptian calendar, but instead, because it's closer to about 350 holes, we know that it resembles the Greek lunar calendar more closely. So that is the story of how this discovery had developed over the years, but the news of the most recent one had come out, just like a month or two ago. So very cool. It's not common to hear about objects that have been solved after, we know that they were from like 100, 200 BC. And to be fair, that just tells you about how advanced some of the technology from the Greeks and Egyptians were. So that's our first story for the day. And our second story here is going to be about some imaging that James Webb Space Telescope has done again. And usually when I look at articles that pertain to like images that space telescopes have taken, I usually steer away because it's a lot about what you see and not so much about the information behind the image, so that's kind of hard to incorporate in the episodes. But today, we've got something new going on with this image that's come from James Webb Space Telescope, and I feel like I couldn't ignore it. So let's get into it. JWST has of late released new detailed images of the Serpens Nebula and has discovered some new jets coming from tons of protostars in the region. And I believe about a dozen have been identified. And from the image, we can see that the stars have created some pretty illustrious outflows that interact with surrounding gas and dust in the middle ground of the image off to the side. And in fact, the outflows from the jets are actually parallel because they evolved together, like in relatively the same time period, and it's very unlikely to have happened by chance. Uh, One of the quotes that I've pulled from the article I was looking at, which I believe is on the NASA website, it includes this statement here. Astronomers have long assumed that as clouds collapse to form stars, the stars will tend to spin in the same direction, said study co-author Klaus Pontoppidan, hopefully I'm saying that correctly, of NASA's Jet Propulsion Laboratory in a press release. However, this has not been seen so directly before. These aligned, elongated structures are a historical record of the fundamental way that stars are born. So, yeah, just talking about the enhancement of detail that comes with these new images, and this quote highlights something really particularly important about the images that we receive from JWST. It's the fact that they give us visual details that requires astronomers to do like less guesswork on what is really occurring with the protostars in the nebula, because previously, because we were looking at just visual wavelengths, we would only see these objects as like blobs. And so once you get the near and mid infrared capabilities of JWST, then that's not the case anymore, and you get a lot more detail. So now we know that the stars are they have like high rotational velocities, and they create these huge magnetic fields and infrared emissions that are, from molecular hydrogen and carbon monoxide. And to add a cherry on top, actually, you can look to the infrared spectrographs that JWST also has received, are like generated from the data that it's received from this nebula, and it just shows the elements that are at play in this region and a lot of the chemistry that's going on there. A quote from the site again. Looking at the abundance of these critical compounds in protostars just before their protoplanetary disks have formed could help us understand how unique the circumstances were when our own solar system formed, said Pontoppidan. So, yeah, that's an article that I found about this beautiful image of the Serpens Nebula. Again, hopefully I will make that the cover art for the episode, just so that you all are not left to be confused. So the last article that we're talking about here is about the evolution of black holes and a new revolutionary simulation that has allowed us to understand this idea here. A team of Caltech astrophysicists have ran some simulations of primordial gas entering a supermassive black hole, and it's actually very, very groundbreaking. The simulation bridged the gap between two long-term Caltech collaborations, which studied the larger and smaller scales of the universe, and they were respectively known as FIRE and StarForge. I know FIRE stands for what was it, like something a realistic environments. I don't remember the like full acronym, but Starforge, I'm actually like genuinely not familiar with what that's supposed to represent. So anyways, these are two collaborations or simulations that studied the larger and smaller scales of the universe, and together they're like put together to create what is known as Gizmo. And so off the bat, we're talking about some massive findings, or at least the potential for it. And the main takeaway from the simulation was that the role of magnetic fields in the formation and evolution of black holes is and has been very underestimated. They've been found to be crucial in the formation of accretion disks, even though since like the 1970s we thought that it was something to do with the thermal pressure from the gas, and that was thought to be the prime component, but really it's the magnetic fields that's keeping the accretion disks together. The simulation also produced huge details on the gravitational influence of the accretion disk because it's got like an immeasurable mass, like millions, maybe even billions of times like more than the sun. So yeah, those are the two main details. Other than that, the simulation went on to confirm some ideas about what the matter around a black hole looks like. It's uh, pretty radiant, and it tends to swirl around instead of just completely falling in, which I feel like we've talked about with quasars before. But if you happen to forget, or perhaps I'm just, thinking of something else, then that is sort of the explanation for the matter that's around a black hole, a supermassive black hole to be specific. The article that Caltech released put a lot of emphasis on the calculation of every intricacy that comes with running a simulation like this, and like exactly how matter interacts to create any stars at the atomic level and all of that stuff, which is why when you have a simulation that puts large scale interactions and small scale interactions together, which is usually a supercomputer simulation, it's a huge, huge deal. And just thinking about the amount of code that you have to use to develop something like this would make one want to faint. That is definitely something that would be unimaginable. But it was done, and there's a lot of perks to doing it this way. Like, first of all, you can put together the two simulation projects, or like, and make them function like stacking Legos, where they're interchangeable modules that you can turn on and off or tweak when you need it. But most importantly, and this is a quote that I've pulled from the article itself, this allowed the scientists in the latest work to simulate a black hole that is about 10 million times the mass of our sun, which is gigantic. You don't have to take my word for it. Just think about the number 10 million times. And, the mass of the sun is huge, obviously. The simulation then zooms in on that black hole at a moment when a giant stream of material is torn off a cloud of star forming gas and begins to swirl around the supermassive black hole. The simulation can continue zooming in, resolving a finer area at each step as it follows the gas on its way toward the hole. So, some truly spectacular stuff that, has happened as a result of a lot of coding and a lot of programming, but it does a lot of important things for astrophysics. Like, we now know that magnetic fields is at play when we're looking at accretion disks, and that's more of the pressure creator. So we'll have to rework some of the analysis that we do on these objects in the future for sure. And there's a lot more that is possible with this simulation, like looking at galaxy mergers. If you can zoom into galaxy merging and like the gravitational interactions, that'll be very, very important in the future. So really, really important simulation that's been developed by some Caltech astrophysicists. And that is the end of this episode here. Hopefully you all enjoyed listening to this one. I try to bring in some more interesting articles and some more interesting takes on the articles just for you. I know some of you may have been missing the content when I was gone for a while, so hopefully this episode makes you a little bit more happy with the level of content that's coming out. I will let you know that at this point in time, I have recorded the shorts that I want to publish. It's just a matter of video editing because instead of clipping all of the content from my regular episodes, I'm actually individually recording the shorts. So those will be coming soon. And yeah, that's the end of the episode. If y'all enjoyed listening to the episode and you're new around here, make sure to drop me a subscribe on YouTube if you're listening there. If you're listening on Spotify, no worries. Just hit me with a follow and you'll be able to see the upcoming episodes. Obviously, I did mention that after, an episode or two, I probably won't get back to creating content until like September. So at least subscribe for recommended content of mine that is a little bit old, perhaps, I guess. Anyways, until I see you all next time, peace.